Mensonge global de Léopathie, chapitre 7. Expériences, instruments, lois et effets. L'échec de Airy. Astronome britannique G.B. Airy utilisa en 1871 un télescope rempli d'eau comme méthode pour ralentir la lumière des étoiles, afin de confirmer le modèle héliocentrique. Malheureusement, pour les partisans du globe, le télescope rempli d'eau de Airy n'a pas prouvé le modèle copernicien et a confirmé le géocentrisme. Bien sûr, des excuses officielles ont été avancées, mais le résultat de l'expérience ratée demeure.
Pointing at a star, and both are stationary, then obviously the light comes straight into the telescope. In 1729, Bradley found that he had to tip his telescope forward very slightly to get a star in the center of his telescope. It was assumed that this was due to the motion of the Earth around the Sun. Let us assume that the telescope was moving at 5 miles an hour and had to be tipped 5 degrees. This 5-degree tipping, however, could equally be caused by the ether moving at 5 miles an hour, carrying the stars around the Earth. As we see here, the light would be coming in at the same angle, and the telescope would still have to be tipped 5 degrees. So tipping the telescope does not tell us whether it is the starlight moving or the telescope moving. However, there is a simple experiment that can determine whether it was the Earth that was moving or the ether and starlight. All that you had to do was record the tipping required for any particular star, then fill the telescope with water, which greatly slows down the speed of light in the telescope. So here is the moving telescope filled with water, tipped at 5 degrees, and you can see that the starlight does not now reach the eyepiece at the bottom. This is because the starlight moves much more slowly when passing through water. However, if the telescope is tipped further, say 10 degrees, then the starlight will then be visible again in the eyepiece. It has to be tipped further because the light is now slower when in the telescope. But if the starlight is going past the telescope at 5 miles an hour, then when it is filled with water, no further tipping is needed because the light is coming in at 5 degrees anyway. The starlight stays on the same path but is only traveling slower in the water. To recap, if it is the telescope that is moving, then when it is filled with water, it has to be tipped further to see the star. If the telescope is stationary and the starlight drifting past us, then it does not have to be tipped further. In 1871, George Biddle Airy, the Astronomer Royal, performed this experiment. This is a copy from his original report. You can see that the two readings are virtually identical. If it had been the telescope that was moving, Airy expected a figure of 30 seconds of arc. In fact, he only managed to read 0.8 seconds of arc difference.
Le test du canon. Il y a plusieurs années, afin de prouver que la Terre était plate et fixe, les chercheurs de la International Flat Earth Society effectuèrent une série de tirs de canon directement dans l'air. Étonnamment, tous les boulets de canon retombèrent juste à côté des canons et certains finissaient même par revenir directement dans le fût des canons. Une expérience reproductible. Ainsi, ces chercheurs en ont conclu que la Terre ne tourne pas à 1600 km/h, auquel cas tous les boulets auraient dû atterrir à l'ouest. Ces boulets de canon, étant très denses, auraient dû contrecarrer une grande partie du mouvement présumé vers l'est de l'atmosphère. Dans cette vidéo, The Morgile discute de cette expérience.
On a length of string, when you let go of the string, what happens? The weight will travel in a straight line. As you spin the weight and let go, the kinetic energy is released and the spin is severed. The laws of motion dictate that the weight will maintain its forward velocity. Try to keep this in mind when considering the flat Earth. Okay? This is a law of physics. International Flat Earth Research Society, I first documented the results of a study that I thought was very impressive about multiple cannons firing simultaneously, perfectly vertical. Now, this is what you should see on the spinning Earth. Remember the string. The ball is going to go straight when it's released from the spin, okay? So, the Earth traveling east at 1,000 miles per hour, the cannon is going to travel away from the point where it was fired. Okay, so just like the string, the spinning force is severed, and the abundant force of the explosion, if you're talking about the laws of motion, we're talking about some other force that would count, okay? Now, what you saw is how it should work, or what you should see on the spinning globe. Now, during the actual experiment that was done under controlled conditions, again, multiple cannons simultaneously, invariably, the ball landed within a couple of feet of the cannon that fired it. And in many cases, the ball landed directly back into the barrel of the cannon that fired it. Okay? So, you know, you can talk to me all you want about you're a physics professor. I don't give a shit. You're a brainwashed physics professor or whatever it is, you Ivy League, whatever. This proves, and you can't argue with this, that our Earth is not a spinning globe. And people are still clinging to the false globe model in their brain, and they're going to try to argue this point with total nonsense. Total nonsense. I don't care what books you copy and paste from, what online, what you copy and paste from. You don't know what you're talking about. You don't comprehend it.
Gyroscope est instrument de navigation. Cet argument peut sembler un peu technique, mais il est relativement simple à comprendre si vous y réfléchissez quelques instants. Essentiellement, un gyroscope, tel qu'utilisé dans les faits, ne peut fonctionner sur un globe car, une fois qu'il commence à tourner, il ne change pas son plan de rotation, rigidité dans l'espace, quelle que soit la courbure de la Terre. Selon le site Wikipédia, une fois qu'il tourne, l'orientation de l'axe n'est pas affectée par l'inclinaison ou la rotation de l'assemblage, selon le principe de conservation du moment angulaire. Du fait de ce principe, un gyroscope ne sera donc pas affecté par l'inclinaison ou la rotation dans un avion, constituant un horizon artificiel. Il peut fonctionner sur un globe puisque l'horizon artificiel ne peut jamais s'ajuster automatiquement à la courbure terrestre. Et en très peu de temps, les indications de l'appareil seraient incorrectes puisque l'horizon artificiel se trouverait à un angle vertical complètement différent. De la même façon, durant un laps de temps donné, par exemple 6 heures, un gyroscope, même posé sur la table de votre salon, mais tournant durant tout ce temps grâce à un moteur, devrait montrer un changement dans la courbure à cause de la supposée rotation de la Terre. Au lieu de cela, les gyroscopes montrent continuellement qu'il n'y a pas de courbure ou de rotation. Imaginez que vous êtes pilote. Quand vous démarrez votre appareil, le gyroscope démarre aussi. L'angle horizontal est maintenant fixé et ne changera plus tout le temps que le gyroscope tourne. C'est très pratique puisque vous pouvez faire des tonneaux et des loopings avec votre avion sans même regarder l'horizon réel. Vous savez où se trouve l'horizon simplement en regardant votre indicateur horizontal. Alors, quel est le problème? Si l'avion s'ajuste automatiquement à la courbure de la Terre du fait de la gravité, ce qui en soi est déjà absurde, le gyroscope ne pourra pas s'ajuster de manière identique puisque son plan horizontal est rigide dans l'espace. Si l'avion descend pour suivre la courbure, le gyroscope gardera l'angle exact qu'il avait en démarrant. Ce changement d'angle serait dangereux pour les pilotes et deviendrait évident en très peu de temps du vol. On sait que Léon Foucault a soi-disant utilisé un gyroscope dans une expérience réalisée en 1852 pour prouver la rotation de la Terre. D'après Wikipédia, c'est Foucault qui a donné à l'appareil son nom moderne lors d'une expérience pour constater la rotation de la Terre qui était visible à 8 à 10 minutes avant que les frictions ne ralentissent la rotation de l'appareil. Toutefois, les gyroscopes de haute précision prouvent la fausseté de l'expérience de Foucault.
Rigidity in space refers to a gyro's ability to remain in a fixed position in the plane in which it is spinning. By mounting the gyroscope on a set of gimbal rings, the gyro is able to rotate freely in any direction. Thus, if the gimbal ring rotates, the spinning gyro will remain in the same plane in which it was originally spinning. Attitude indicator. An attitude indicator is an instrument used to inform the pilot of the orientation or attitude of the aircraft relative to Earth. It indicates pitch, which is the fore and aft tilt, and bank or roll, which is the side-to-side tilt. Through the use of an artificial horizon and miniature airplane, the instrument depicts the position of the airplane in relation to the true horizon.
The other type, known as apparent drift, relates to rigidity in space. Once again, consider this condition. The gyro maintains its attitude while the Earth turns under it. Every 6 hours, the gyro drifts through 90 degrees in relation to the Earth's surface.
But the thing that really got me interested was, as you say, the gyroscope. In a plane, there is an artificial horizon, okay, and it's based on a gyroscope. And if you spin a gyroscope on a surface, it will want to stay upright. You can twist and tilt the surface as much as you like, the gyroscope will stay upright. So, if a plane has a gyroscope and it starts following the curve of the Earth, the gyroscope would stay upright, which means the artificial horizon will start to roll backwards. But it doesn't. That's absolute proof that a plane flies over a flat surface rather than a curved one.
In a nutshell, what I think it means is that really the only way a gyroscopic navigation system could work is on a flat Earth. I mean, period. Because when you think about what they are saying, what are explaining about how the thing works, and that it does not stay aligned with the surface of the Earth, right? It always has to be. They're talking about how it needs to be adjusted when, a gyroscope is in a vehicle that moves around the Earth. But at the same time, the Earth is constantly moving, so that's going to be throwing you out of alignment from the true up and down as well. So how is a magnetic compass going to know how to, or anything else for that matter, to know how to adjust the gyroscope in relation to the Earth accounting for both the motion, the movement of the vehicle, whether it's a plane or a sub or a ship or whatever, and the motion of the surface of the Earth around the center of the Earth, right? Which is supposedly where gravity is pulling everything down towards, right?
Play-Doh, some kids' plasticine. So I did that. I got some of my daughter's Play-Doh, just spun it up to speed with the motor and then inserted this into the hole. That seemed to do the trick. I was able to balance it perfectly. Before I put this in, the extra weight caused this side to drop every time, and if it was over here, it would drop this way. So that's how I overcame that. I've attached the whole setup to a protractor, which I've blue tacked to the table, and I've blue tacked the actual the frame to the table as well. So this here is the angle that we're looking for. So what we're looking for is this effect. See how the gyro wants to rotate and stay in the original orientation? Well, that angle that it's rotating, that this bar appears to be rotating over the vise, that is the angle that we're looking for. That is the angle that we should be able to calculate this gyroscope moving due to the rotation of the Earth underneath us. So without further ado, let's get on to the test. So I've just attached the motor there. It actually takes 4 AA batteries to power it, and I've run this test quite a number of times now and put quite a few batteries through it, so I kind of know how long they're going to last and what sort of sound comes from the motor, depending on how much power is left in the batteries. And I'd say there's about probably 75% power left in them at the minute, and that's based on 12,000 RPM maximum. That's probably about 8,000 or 9,000 RPM for this particular test. So it's getting up to speed now. I'm going to remove the motor and replace it with the piece of Play-Doh to get it perfectly balanced. And now I'm going to demonstrate some precession by gently pressing on the horizontal bar there. And now I'm going to line it up as best I can, so that you cannot see the brass flywheel from above, and it's as sort of straight up and down as possible. So if we just take note of where we are now, you can see a 0 on the top right, just to the right of the bar. You can see a 0 just there, and you'll note that you cannot see the brass flywheel from above now. So we are sort of dead centre above it. So now it's just a waiting game. So while we wait, let's just have a look at a brief history of the gyroscope, up to the point where, near his death, he returned to Roman Catholicism that he had previously abandoned. Draw your own conclusions. So going back to the test, we've exceeded 6 minutes now and there's no observable movement. You can still see the 0 to the right of the bar in its entirety, and you still cannot see the brass flywheel from above. So how much should the gyro have precessed? What angle should the gyro's axis have moved? The calculation is the sine of the latitude times 15 degrees per hour. My current latitude is exactly 53.06 degrees north. So the angle in which the gyro should have moved in 6 minutes is 1.2 degrees. Now this doesn't sound a lot, but let's assume that Leon Fourcault's experiments were performed in Paris. He should have seen even less based on his latitude. And let's not forget that he didn't have an electric motor spinning his gyro up to 9,000 RPM. So I'm just going to stop it now. You saw then that there was still plenty of energy left in that.
Bon, dans cette vidéo, Rob Durham utilise un gyroscope très perfectionné pour prouver que les gyroscopes ne mesurent pas la courbure et que la capacité du pendule de Foucault à mesurer la rotation de la Terre est fausse.
So in order for the pendulum to work effectively, it requires a really tall building to suspend it from. Typically 15 metres upwards is ideal, but the longer the better. And they do appear to exist in the northern and in the southern hemisphere, and they do indeed, by all accounts, spin anti-clockwise in February of 1851 in the Paris Observatory. So let's start in Paris, and we'll draw a yellow line up to the North Pole, and the red line represents the rotational direction of the Earth to the east. We'll put on there the pendulum, a much larger pendulum, and the two balls, the orange balls, represent the extremities of the swing of the pendulum. Notice they are aligned with the north, so as the Earth rotates to the east, the pendulum wants to stay in the direction that it was originally swung, and the North Pole is still pointing north. So if you measure the angular difference between the first point and the second point, shown in green, you'll find that the angular speed is proportional to the sign of the latitude. Meaning if you were kidnapped and flown to a secret location and put in a room with only a Foucault's pendulum, a clock and a calculator, you should be able to determine exactly the latitude that you're at on the Earth. Now some Foucault pendulums, like the one in this picture, they have the 4 cardinal points marked on them, and some have the individual degrees, the 360 degrees in between as well. My point being that the effects of the Foucault pendulum aren't just confined to the room that the pendulum's within. For instance, that north line there will extend out of the room and continue all the way to the North Pole. And at any given point along that line, the exact same principles that are occurring within the room the pendulum is in itself is occurring along that entire line, albeit at varying different angular velocities depending on your latitude. Logically then, if we were to scale, we should have rotated by exactly north. After 1 hour, will we still be travelling north, or will we be travelling northeast as the Foucault pendulum would dictate? Well, according to the maths, at a latitude of 50 degrees in northern France, we should have rotated by about 11.5 degrees to the east in our giant swinging pendulum. After all, during the swing of the pendulum, it just wants to go in the direction it was originally swung. As high as I can get with my tripod. And there's a bob on the bottom, and I've fixed it to this platform that rotates. So I just want to show the effect of the Foucault's pendulum. So this would represent your destination, i.e. northern France. Let's say that's southern France. And let's set the pendulum off going straight as we can, and in one swing I'm going to rotate this platform very slightly to show the effect. So here we go. So it's moved, apparently the destination's moved left, and this pendulum is still swinging in the original direction that it was launched from. So that would be the 11.5 degree difference that we calculated earlier. So I want to just point out that this motion here, that the fact that it appears to spin on the spot, it's not through any external force what is proposed. This is just purely where it wants to go. No force is being applied anywhere. The Coriolis effect is exactly that, an effect. The Coriolis acts on nothing. It's just an outcome, a visual outcome of what happens when an object moving at a velocity across another rotating object. That's all it is. So the Coriolis is just an effect. It's acting on nothing. There's nothing, no force acting to make it go in that, to make it spin. So what I want to know is, what is different about this mass than any other mass on this planet? What is it that's different about a pendulum that differs from a plane? If this was an aeroplane, if we go back and say that's the destination, this is an aeroplane, the aeroplane does this. The Foucault's pendulum does this. Why? What's different about this mass to an aeroplane?
Le problème de la boussole. La façon dont une boussole fonctionne sur un globe est problématique. Par exemple, une personne utilisant une boussole en Amérique du Sud aura du mal à trouver le nord. Pourquoi? Parce que le nord magnétique devrait se trouver à peu près sous ses pieds, c'est-à-dire directement en direction du sol. L'aiguille d'une boussole s'aligne d'elle-même et pointe vers le sommet du champ magnétique terrestre, qui est à présent supposément au-dessus de l'extrême nord de la Russie. Cependant, il n'y a pas d'indication que les boussoles aient plus de difficultés à trouver le nord dans le sud du Chili, l'Afrique du Sud ou l'Australie, où s'alignent jamais en direction du centre de la Terre. L'effet Coriolis prouve la Terre plate. L'effet Coriolis est souvent avancé par les tenants du globe comme une des meilleures preuves de la rotondité de la Terre. En réalité, cet argument apporte bien plus de crédit au modèle de la Terre plate et n'aurait absolument aucun sens sur un globe. Si l'atmosphère de la Terre tourne en rotation synchronisée avec le sol du fait de la gravité, l'effet Coriolis ne devrait dès lors pas exister. L'effet Coriolis est censé impacter les balles et faire tourbillonner les ouragans, soit dans le sens des aiguilles d'une montre, soit dans le sens inverse. Pourtant, il n'a aucun effet sur le vol de l'avion, sur les parachutistes, sur les ballons météo ou sur les éruptions volcaniques montant droit dans les airs. C'est comme si l'effet Coriolis était sélectif. Voici une vidéo semi-officielle qui décrit l'effet Coriolis et la façon dont il est supposé fonctionner sur le modèle du globe, sur les phénomènes météorologiques et les avions notamment. Mais les vidéos suivantes montrent comment l'effet Coriolis échoue sur le globe.
The air rushing toward the center is deflected off course.
Let's ask a critical question here. And this is necessary, and this is what makes science's explanation for Coriolis absolutely ridiculous. What if this low pressure system here is not moving? So it's not moving from a faster to a slower location on the Earth. According to science's own definition, there's no reason for the air then to deflect, because what is causing it is not happening. Do you understand that? There are plenty of times, especially as storms get very strong, they don't have to be hurricanes. They can be what are called cut-off low-pressure systems, where they can be just in one area for quite a long time, just drifting back and forth, north, south, east, and west, not really going anywhere for days at a time. Why is that spin happening then? It's not moving from a one conservation of energy to a lower one, a higher to a lower conservation of energy type of deal like they were explaining before. Let's add one more scenario in here, which happens very often with hurricanes. What if the hurricane moves due west, comes off the coast of Africa as a low pressure system? this happens all the time, folks, moves almost purely due west towards the southern United States, the Gulf of Mexico area, due east to due west. So it is not moving from faster to slower. It's moving from the same speed to the same speed. Okay, it is time for a little review.
Question 8. Why is the Coriolis effect so selective? This is an explanation of the Coriolis effect by a gun expert.
And one of the common issues that we see is the Coriolis effect. And what guys are not doing is taking into account the effect that this can have on your shooting at longer ranges. Now, real quick, let's kind of just explain the Coriolis effect in layman's terms. The Coriolis effect is the effect that when the bullet leaves the barrel of the gun, it is actually leaving the surface of the earth. So as the bullet leaves the barrel of the gun, the earth is still rotating, and the bullet is not rotating with the earth. So the earth will actually rotate out from underneath of the bullet while it is in flight.
So bullets and artillery shells no longer rotate with the earth when they leave the surface. And according to this explanation, paper aeroplanes act in the same way.
So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right.
If this is the case for bullets, artillery shells and paper airplanes, then why is it not the same for real aeroplanes? Airplanes do not aim north to go east. In fact, if aircraft no longer rotate with the Earth when they leave the surface, then east to west flights should take much longer than west to east flights. And landing on a moving runway would seem to be quite tricky. Every landing should be like this. And wouldn't there be planetary direction indicators by runways, just like there are wind direction indicators?
La farce de la gravité. Comme nous l'avons déjà vu, la gravité a la capacité de nous empêcher d'être éjectés d'un globe tournant à 1674 km/h, tout en étant capable également d'adapter ses effets sur les objets ou les gens suivant sa position entre des pôles, où la force centripète a une magnitude différente. Cela ne s'arrête pas là puisque la Terre est supposée tourner autour du Soleil à 1800 000 km/h tout en tournant sur elle-même à 1674 km/h. Si vous vous trouvez sur le côté de la Terre, dans le sens du déplacement de celle-ci sur son orbite, le sol sous vos pieds fonce à environ 109 674 km/h, comme si vous vous retrouviez sur un élévateur s'élevant à toute vitesse. Si au contraire, vous êtes du côté opposé, au sens de la rotation de la Terre autour du Soleil, le sol s'éloigne de vous environ 900 674 km/h, et c'est comme si l'élévateur chutait à toute vitesse. Dans un avion ou un train, vous sentiriez certainement la différence, mais pourquoi pas sur la Terre qui va beaucoup plus vite? La gravité peut expliquer La gravité ne peut expliquer cette absence d'effet physique. De plus, si la Terre tourne, sa vitesse devrait augmenter quand elle se déplace en direction de l'orbite et diminuer dans la direction opposée. Pourtant, personne n'a jamais noté, ressenti ou mesuré ces changements qui devraient se produire en permanence. La gravité telle que communément admise n'existe tout simplement pas, et vous pouvez le vérifier par vous-même. Tenez-vous debout à côté d'une grande montagne ou d'une falaise et suspendez une pierre au bout d'une ficelle. Est-ce que la pierre va se déplacer horizontalement vers la montagne? Pas du tout. Même si vous la placez à quelques millimètres seulement, la pierre prend perpendiculairement vers le sol et la montagne n'exerce pas la moindre attraction sur elle. L'expérience de Cavendish est une autre fraude perpétuée par la science officielle. Les deux vidéos suivantes illustrent cela, avec d'autres exemples prouvant la supercherie de la gravité.
I'll be looking at gravity and its practical application. In other words, when we try and apply what we've been taught about gravity, does it work? And if not, why would they lie to us about gravity from the get-go? See, we're told that Isaac Newton was sitting under an apple tree and an apple fell on his head, and then he discovered gravity. But yet, all the people before him somehow never noticed that heavy things fall down, and they were able to build massive buildings. Then you realize that Isaac Newton belonged to a special club and was heavily involved in mysticism, alchemy. Another word for this is sorcery. He was a wizard. So, would a wizard share his secrets with you?
S'agissant de l'expérience de Cavendish, regardez donc cette vidéo.
Represented by these lead balls. At the back of it, he had a big garden shed, which might seem like the size of my house. And in it, he had two lead balls, like this, suspended from the ceiling. Only this is not to scale. This is, lead balls. Now, the real problem is that he wanted to measure the attraction between two objects due to gravity. In other words, there's a gravitational attraction between you and me, or between me and this lead ball.
So gravity, which is a theory, and was only invented because they said that the Earth spins, and it's needed to explain why things don't go flying off the spinning Earth. And as far as I know, this is the only so-called experiment, like this chap's explaining, that gravity, according to them, is all objects of mass are pulling towards each other. And so this experiment is supposed to demonstrate that. So let's see.
So he had to be a long way away to look at the experiment, otherwise he'd interfere with it. So he had an aperture, a place where he looked through, and he put a telescope out there, and he stood outside in all weathers, and he was in his 60s doing this, staring through the window to take his measurements over a year. There's another set of lead balls inside there. This experiment really is very difficult to get to work, and a technician has sawed it apart because he got so frustrated.
Yeah, I don't think I need to say much else, do I? The technician got frustrated, so he sawed it apart because it doesn't work. Brilliant. So if you're having a debate with anybody about gravity, okay, and they try and throw this in your face, just send them to this video. Cavendish experiment, 60 symbols. This is such a good experiment that they can't even replicate it without taking a hacksaw to it.
And then right in the middle there's a bit of glass, there's a mirror which should be suspended from a torsion wire. So you'd set it up like this in his shed, and you put it like that, and this lead ball would attract that lead ball, and this lead ball would attract this one. And so it would be pushed a little bit this way and twist the wire, and that would be pushed a little bit that way. And the wire would twist, and as the wire twists, the mirror, which is dangling in there, would twist a little bit, and light which comes in would be reflected off at a slightly different angle. And all he had to do was measure the angle. He then had to move it the other way round. Oh, he didn't move this bit. He moved the lead balls round so that you had an equal and opposite effect on the other side. So instead of having, you'd have that configuration. He had this is a very complicated technical thing for the time. This experiment really is very difficult to get to work, and a technician has sawed it apart because he got so frustrated. 18th century we're talking about, and he put that way round, and then it was pushed the other way, and you could then see the displacement. Moreover, you could measure the period of oscillation of this, and from that get all the properties of the wire, the torsional constant. And that enabled him to measure big G, the gravitational constant, to an accuracy of 1%. And nobody improved on that for 100 years. He didn't describe it as that. He described it as though he was weighing the Earth. He was calculating the mass of the Earth, so that when you're attracted to the Earth through gravity, it's the product of the mass of the Earth, this big gravitational constant, divided by r squared, the radius of the Earth squared, which we normally know as acceleration due to gravity. And that quantity is essentially big G, and he measured it. And nobody could do a clever experiment. So he's a father of physics, experimental physics, some of the ideas of theoretical physics.